Okay, so we will be starting this lecture from the Cauchy's first theorem itself. In the last lecture, I could not have discussed in details about the Cauchy's first theorem. Uh, I am rediscussing this in this lecture so that we can, revise what we had done in the previous part, as well as we can go through the proof of this lecture. This theorem. So Cauchy's sequences we have already discussed. That is a sequence AN is a Cauchy sequence if for all epsilon greater than 0 there exists some n naught belongs to n such that m and n greater than n naught implies difference between am and an and its modulus will be less than epsilon, right, for all m and n. This is what we know by Cauchy sequences. And further we studied that a sequence if convergent is a Cauchy sequence is a Cauchy sequence and converse, right? All Cauchy sequences are counted. With these things we have studied. In the previous lecture, I had given the statement of the Cauchy's first theorem, which says that limit n tends to infinity xn. Okay, xn is basically a sequence, a real sequence given. Not sorry, sorry. If this is equals to L, then that implies limit n tends to infinity summation r equals to 1 to n xr by n is also equals to, right? L is the limit of this function. Got it? And xn is a real sequence. Got it? Okay. So, any arbitrary sequence we are talking about here. Let us see the proof of this particular theorem first, and then we will be moving on with the lecture. I mean, we will be solving one or two questions of this. First, let us see the proof. Proof is important to understand. Here we use a simple substitution trick. We will do it right now. So, proof. Okay. So, let an be a sequence such that an is equals to L plus some bn where limit n tends to infinity an is equals to L. Then this implies limit n tends to infinity bn is equals to 0, which further implies that the sequence bn is convergent, right? The sequence bn is convergent. Okay. So we will use this fact itself. Okay. Now, so we got C. So we can say that A1 is equals to L plus B1, A2 is equals to L plus B2, and we can continue like this, right? And then we get an is equals to L plus bn, and upon adding all of them, what we get that a1 plus a2 so on plus an upon n is equals to L plus b1 plus b2 so on, right? This is what we get. Clear? We bring the L on the LHS. So from here we can say summation r equals to 1 to n ar upon n minus L is equals to summation r equals to 1 to n br over n. This much is clear. Okay. One more thing, let us do it here only. See, since b in this sequence is convergent and its limit is 0, so from here what can we say? Mod of bn minus 0 is less than epsilon over 2 for all epsilon greater than 0 and n greater than some n naught. Clear? Got it? This we can say. So from basically here, from here what we get is that Bn, its mod is less than epsilon over 2. Got it? Let us keep this like this. Achha, one more thing, since it is convergent, it is also bounded, right? It is being it is convergent, it becomes a Cauchy sequence, and Cauchy sequences are bounded. So we can say also the sequence Bn is bounded. Okay. So let Bn, mod of Bn be less than equals to m. So simply let's say Bn is less than equals to m. Let m be its upper bound. Okay. Let Bn be less than equals to m. Okay, this much is clear. Okay, now let's come back to what we were doing. Acha, see, if I put modulus on both the sides, what will I get? So mod of summation r equals to 1 to n ar over n minus l is equals to mod of. Acha, we break this addition in this form. Let's see. So summation r equals to 1, okay, to this n naught. Okay, r equals to 1 to this n naught br over n plus summation br r is equals to n naught plus 1. Okay, r is equals to n naught plus 1, and here you have n by, okay, this much is clear. So by the triangle equality we can say this is less than equals to mod of summation r is equals to 1 to n naught br over n plus summation r is equals to n naught plus 1 to n br by. Is this much clear? Got it? So now see, acha, see, let us analyze this sequence first. So b1 plus b2 and so on till bn naught by n. Acha, each of these terms is less than m, capital M, because capital M is the upper bound. So we can say that this is less than equals to, so we have n naught times m by n. We can put it here, right? So which is further less than equals to n naught times m by n plus. Acha, when you have n is greater than n naught, when you have n is greater than n naught, then each of these terms basically will be less than epsilon over 2. Number of terms is n minus n naught by n. Each of these terms will be less than epsilon over 2 by the definition of convergence from here we got. So each of these terms is less than epsilon over 2, and there are n minus n naught terms, so we get this times epsilon over 2. Clear? Acha. Now what happens, see, since n is greater than n naught, so n minus n naught by n, which is equals to 1 minus n naught over n. Okay, so this is basically greater than 0 and less than equals to 1. Okay, or let us not say it's less than equals to 1. Let's say it's less than 1. Let us not put n naught as 0. Okay, it is less than 1. So basically it is around 1. So this particular inequality helps us neglect this term. So neglecting this term, what we can say, so this is less than equals to n naught m over n plus epsilon over 2. Is this much clear? Now here what we do is that it is very simple to see. So see, if n naught is a fixed integer, okay, if we keep n naught fixed, then let n naught m over n is less than epsilon over 2. And from here what can we say? That n is greater than 2 n naught m by epsilon. Okay, so therefore we can obviously choose some value of n such that is always greater than 2 n naught m by epsilon by the Archimedean principle, right? So this basically ends our proof. So what we do is that we choose this n in such a way, so we choose we choose this n naught belongs to n such that n greater than n naught implies n is greater than 2 n naught m by epsilon, and if so, then we can change this inequality to less than epsilon over 2 plus epsilon over 2, which is less than epsilon, right? So from here what can we basically do? So from here we can basically say that mod of a1 plus a2 and so on till an upon n minus l is less than epsilon for all epsilon greater than 0 and n greater than n naught, right? So from here we can say limit n tends to infinity a1 plus a2 plus so on till an over n equals to. Got it? Clear? So this is the proof of the first Cauchy sequential theorem. Okay. Acha, I had previously in the previous lecture itself I had done a sum which had the application of these Cauchy sequence. Okay. So in this lecture, so this was basically the proof of the Cauchy's first theorem. Okay. Acha, in this lecture we will be starting with the second Cauchy's theorem. Okay. Second theorem of Cauchy. So let's see that. So let me give the heading here. So Cauchy's second theorem. Yeah. One second. Let me drink some water. One second. Okay. So okay. So as we were discussing Cauchy's second theorem. So there are two statements basically. Let us first discuss the first statement. The first statement basically says that limit n tends to infinity xn is equals to L. This implies limit n tends to infinity x1 times x2 and so on till xn is to the power 1 over n is also equals to L. Okay, a had xn is greater than 0. Clear? This is the Cauchy's second theorem statement. Very obvious statement. Can you can basically compare this with the Cauchy's first theorem. Putting a logarithm to this will help you understand this theorem using the Cauchy's first statement. You can do it on your own. You can check this on your own. How you can observe this using the Cauchy's first theorem of sequence. So this is very simply the Cauchy's second theorem. Let us solve a problem regarding this. Then we will be moving on to the second statement of Cauchy's second theorem. Okay. So let's take this question. So limit n tends to infinity. Okay. Limit n tends to infinity. We have 2 by 3 sorry into 3 by 4 so on n by n plus 1 whole to the power 1 by n. So how to find the limit of this problem? Very easy. Okay, let us take this as the nth term. So let xn is equals to n over n plus 1. So this implies limit n tends to infinity xn is equals to limit n tends to infinity n over n plus 1, which is equals to limit n tends to infinity 1 over 1 plus 1 by n. This becomes 0 as n tends to infinity, so this is equals to 1, right? This is equals to 1. So this is the nth term, so we are getting, so what is this one? So this is, if this is xn, then this is x1, this is x2, right? Okay, this is 2, sorry, not x1, this is x2, this is x3. Achha, let us add one more term to it, 1 by 2, I missed that term here, right? Okay, 1 by 2, sorry. So 1 by 2 to 2 by 3, and yeah, now it's okay. So from here, so this is x1, this is x2, x3 and so on. So from here what we get? So this basically implies that your limit n tends to infinity 1 by 2 times 2 by 3 and so on n over n plus 1 whole to the power 1 by n is equals to. Clear? Cauchy's second statement. Okay. Okay. Let's see the second statement of Cauchy. Okay. Second statement. The second statement says, let xn be a sequence such that xn is greater than 0 and limit n tends to infinity xn plus 1 by xn is equals to n, where l is greater than 0. Where l is greater than 0. This implies limit n tends to infinity xn whole to the power 1 over n is also. Acha, in this basic concept is where l can be finite or infinite. In the previous ones we had basically assumed, though I had not kind of verbally kind of told it here directly, but there if you see the proof, you can obviously see that l was there taken to be a finite number. Okay, so it can be finite or infinite in this case. Clear? So let's see how this proof helps us. So you have a sequence xn, okay, where every term is positive. You find this limit xn plus 1 over xn where l is greater than 0. So finding this will help you find this particular limit xn whole to the power 1 over n. That will be equal to l itself. Okay. Let's solve a problem using this. Okay. So suppose let's say question limit n tends to infinity. So here we are not asked to here we are not basically given this as a sequence. Here we are given as a normal limit, okay, a single term limit. So you are given this n factorial whole to the power 1 over. How to solve this? So this is your xn, right? This is your xn. So if basically xn is equals to n factorial, what will be the value of xn plus 1? N plus 1 factorial. So limit n tends to infinity xn plus 1 by xn is equals to limit n tends to infinity n plus 1 factorial over n factorial is equals to n plus 1. So this is equals to infinite. So this implies what? So the L is thus greater than 0. So this implies limit n tends to infinity n factorial whole to the power 1 over n is also clear. Got it? In this way you can also solve the problem like this. Let's say when n tends to infinity n plus 1 into n plus 2 so on till you have here n plus n divided by n to the power n, okay, whole to the power 1 over 1 by. So here this will be your xn, right? Here this will be your xn. So you need to find limit n tends to infinity this plus 1, right? So what is this plus 1? N plus 1, n plus 2 so on, n plus n, and then what you have? N plus n plus 1, right? So 2n plus 1, let's say 2n plus 1 divided by, okay, n plus 1 to the power n plus 1, right, by, so here you have n plus 1, n plus 2 and so on till n plus n by n to the power n. Clear? So what do you get from here? So limit n tends to infinity. Acha, so this part and this part gets cancelled. So we have 2n plus 1 into, what do we have here? N to the power n over n plus 1 whole to the power n plus 1. Right? This is what we have. Clear? Achha, what we can do here basically, let us divide, let's say we divide the above and bottom with n to the power n plus 1. What we will be having? We divide this. So limit n tends to infinity. So if we divide the above with n to the power n plus 1, what do we get? So let us put here, so 2 plus 1 by n, and here what do we have? So n to the power n, right? So this becomes 1 times 1. 1 n we distribute here, we divide this by 1 n, and the other part we give here. So bottom also you have n to the power n plus 1, right? So we put inside, so we get 1 plus 1 by n whole to the power n plus 1. So this becomes 0, this becomes 0, right? Acha, this becomes 0, this becomes 0, and in the bottom you have n plus 1 power. Clear? Acha, 1 plus 1 by n whole to the power n plus 1. This can be written as 1 plus 1 by n times n into 1 plus 1 by n, right? Acha, n tends to 0, n tends to infinity, limit n tends to infinity, this is equals to e, right? This is equals to e, this is equals to 1. Above you have 2, so this becomes 2 over e into 1. So this is 2 times e to the power minus 1. This is also, so here basically what you have, so this is your L is equals to 2 times e to the power minus 1, which is plus greater than 0. So that implies to limit n tends to infinity, whatever you had, right? What you had, n plus 1, so on till n plus n by n to the power n whole to the power 1 over n is equals to 2 e to the power minus 1. Clear? So this was all for today's lecture, guys. In the next lecture we will be discussing about infinite series, I guess. So meet you guys in the next lecture.